Hey all, this is our second project for statics at Northwest Vista. What we have here, sketched in AutoCAD, is a representation of the San Antonio and Aransas Pass Railway Bridge just east of Comfort, Texas. This is the shortest and southernmost span, a fairly simple 150-foot Warren Truss bridge with a couple added verticals which help support the top chord. There are 6 25-foot bays, and the height was estimated at 30 feet, which is just short of a 345 triple, but a bit more practical. There were two parts to estimating the load on this truss, adding up the dead load, the external part of it, I'll get back to that, and the live load. For our dead load, we chose to just take the weight of the track structure. Using the standard tie spacing of 19.5 inches, we get about 93 ties in a 150-foot section. And estimating the weight of a 7 by 9 inch by 8 foot tie to be 200 pounds, we get 18,600 pounds of ties. And using two lengths of standard 135 pound per yard rail, that's 13,500 pounds of rail, which makes for a total of 32,100 pounds. Since we're only analyzing one truss section, we assume the loads will be symmetrical across the two sides of the bridge, so we can simply divide all loads by 2. Anyway, from that, we get 107 pounds per foot distributed load. Now to approximate this as a series of nodal loads, we simply split this into 7 equal sections over the joints, except the two ends which are halves, giving us 2,675 pounds and 1,337.5 pounds respectively. As for our live load, we went ahead and considered a train of 286K gross cars, which is the modern standard, as concentrated point loads. If we start having each of these trucks account for half the car weight, and we have 2 of them, we end up right back where we started. But then we half it all in the end, and we end up with 143K pounds over each node, except for the ends again, which are 71.5K. And to get on to our calculations, we of course started with sums of forces and moments to find the reactions, and we'll show worked solutions using both methods of joints and methods of sections.
With one fixed joint at A, we have an AX and an AY, and we are assuming that on the flip side, we have a roller connection support, which would account for thermal changes in the truss. And that would only give us a GY. And in taking these assumptions, we were able to find our final calculations of the forces acting on the truss itself.
Okay, so for our calculations, the key equations we used were the summation of forces in the x direction, the summation of forces in the y direction, and the summation of moments were equal to 0. So taking that into account for our reaction forces, we first isolated the structure, so without all of the internal supports, and we found that A of x is equal to 0 kip. The summation of AY and GY were equal to 445.08 kip. Of course, that's taking into account all of our loads. And then for finding out our y direction forces, reaction forces, we looked at the moments about A, and we were able to find that G of y is equal to 222.54 kip. And then using that previous equation for AY plus GY, we found that AY was the same as GY, that same 222.54 kip.
The method of joints is used to determine the forces in the members of a truss by analyzing each joint individually. I started all the way with pin G, where only 2 or 3 members met, and I started the equilibrium equations where I set my f of x and my f of y equal to 0, and then I applied and solved for the unknown forces, in which then I repeated for each joint all the way up until I found all the force members and the resulting forces.
So for our method of sections calculations, I went ahead and chunked it up into 2 different parts. The first section being cut between KL, EL, and EF. I started from the most rightward hand, going from G, going to F, and then ending at L. And then for the second section, I went ahead and made the right-hand side equal to the left-hand side of the first section. That way, just to make it a little bit easier, since we already calculated those numbers. And then for the left-hand side of the second section, I cut it at IJ, CJ, and CD, and we went ahead and found all of those forces, whether they were in compression or in tension. And then the last step we went ahead and took was assume that our forces were the same on both sides of the truss. So all of our forces here were equal to the ones that we had just calculated, just, mirroring along that middle axis. So, in conclusion, we went ahead and ran a truss simulation just to check our calculations against. We found that all of the members in compression were the most top parts, the outermost members, and then the innermost diagonal members as well. We found that all of the other ones were in tension except for our two vertical supports here, that second and fourth one. And of course, we checked all of our calculations against this simulation, and we found it all to be correct.